So to understand why different metals give different colors, we need to review atomic structure. And so I just want to remind you that the atom has electrons, protons, and neutrons. Protons and neutrons are in the nucleus. Electrons are found outside the nucleus. And so if we think about metals, right, they're atoms, and then we're zooming in on the atoms. I want to remind you the atomic number is the number of protons or electrons, and the mass number is the number of protons plus neutrons, because we're going to focus on the number of electrons quite a bit in this screencast. So let's zoom in. Speaking of that, let's zoom in on those electrons. So we said the electrons are outside the nucleus, but really, where are they? Well, those electrons are in atomic orbitals, and atomic orbitals are just regions in space with a high probability of finding an electron. And so electrons move so rapidly within the orbital, it gives it a high electron density. Okay. Now we have energy levels, and these energy levels outside of the nucleus are regions where electrons may be found. Okay. And we have given them numbers to help identify them. And so we define those energy levels as N. So N is what we use to represent the energy levels. And you can be at an energy level 1, an energy level of 2, an energy level of 3, and so on and so forth. The important thing about energy levels is the larger the energy level or the value of N, the higher the energy level. And the farther away from the nucleus those electrons are. Okay. Now, when we talk about this, we also need to talk about sublevels. So when we talk about energy levels, you're also going to hear this referred to as the principal energy level. And so the number of sublevels in a principal energy level is equal to N. So what do I mean by that? Well, if N is 1, so if we are at energy level 1, there is one sublevel. Right? If N equals 2, there are 2 sublevels. Right? And so on and so forth. Well, we define sublevels as just a set of energy equal orbitals. So when we talk about sublevels, these are just a set of energy equal orbitals within a principal energy level. And sometimes these are called subshells, right? And they increase in energy from S to F. So we use letters here to tell us what the subshells or sublevels are. And so S is the lowest energy and F is the highest. we specify both the principal energy level and the subshell when we describe the location of an electron. So, for example, we would say there's an electron in the 3D subshell. That tells us that the energy level is 3, right? So that's the energy level. And then what the subshell, that D subshell, really tells us is the shape. Okay, so let's look a little bit more at energy levels and subshells. And I have a summary here for you because I know this can get really overwhelming. So if we are at the principal energy level of 1, right, here's 1, and the subshell it would have would be 1s, and that's it. Okay. If we are here at the principal energy level of 2, you are going to have 2 possible subshells. They can be S and P. Both of them get the 2 in front of it. Okay. If you're on the 3rd level here, you're going to have 3 subshells. You can have an S, a P, and a D. All of them have a 3 in front of them. If you are on the 4th level here, you can have a S, a P, a D, and an F, okay? And that's all we are going to deal with. And so that we're not going to have any more. This is really what we are going to end up looking at. Now, in a subshell, there are these atomic orbitals. And when we talk about there being an atomic orbital, the definition there is really just a specific region of a subshell containing a maximum of 2 electrons, and that's super important. Each subshell can only contain 2 electrons. Now, I mentioned before orbitals are named by their sublevel or subshell, right? So sublevel or subshell, used interchangeably, those are synonyms, and the principal energy level. And so they're here. Now, each type of orbital has a characteristic shape. So when we say something is an s orbital, what that tells us is that shape is spherical. That's a spherical space that the electron can be found in around the nucleus. The P is shaped like a dumbbell, right? Or a barbell, or a hand weight, right? If you do a lot of exercising. So let's look at those shapes. So for example, here is the s orbital. What we see is as we increase those energy levels, the area of the s orbital gets bigger, but it's spherical. The P is like a dumbbell, and if we think about an x and a y axis, those are 2D axes that we've seen in like math, or if we've graphed something. You can also have an axis that helps us look into the 3rd dimension, and that's z here. And so that dumbbell shape can be lined up along the x-axis, along the y-axis, or along the z-axis. So we end up with 3 p orbitals that are at the same energy. Now let's look at D. D orbitals are kind of wickedy wild. They look like flowers all the way up into here that looks like a p orbital with a donut. But the take-home message here are there are 5 D orbitals. So we have 1 s orbital shape, we have 3 p orbital shapes, and then we have 5 d orbital shapes. So as a summary, if you are an s subshell, you only get 1 orbital, right? And it is spherical. Right? And a lot of times we show that with like a line or a box. So you'll see like 1s like this, or you'll see a box to represent that as 1s. Okay? If you are a p orbital, you end up with 3 orbitals of the same energy level. So 1, 2, 3, And so this, for example, would be like 2p, where these are the same energy. For D, you end up with 5. So for example, if you are 3D, you would have 5d orbitals at the same energy. So a great question here is, how many electrons can be in the 4D subshell? Well, to answer this, we really need to look at D. When we look at D, we know there are 5 orbitals that the 4D subshell can have, and each orbital has 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we end up with 10 electrons. Each arrow that I'm showing there is an electron. So there's a total of 10 maximum electrons that can be in the 4D subshell. Now let's look at how we can arrange all of the electrons into these atomic orbitals for individual atoms. When we do this, a lot of times is called an electron configuration. And this is just the arrangement of electrons into those atomic orbitals. There's a couple ways to do this. One of the ways to do this is an orbital diagram, where the orbitals are shown as lines or boxes. And the electrons are shown as arrows. Now, when we make these electron configurations or orbital diagrams, we have some rules that we have to follow. The first rule is the Aufbau principle, and it says that electrons fill the lowest energy orbital first. So that means S is going to be filled first, then P, then D, and then F. That's the order we're gonna go in. Then also that means that the energy level 1 is going to be filled before 2, which is going to be filled before 3, right? So that's the order when we think about filling these, that these electron configurations go in. The next rule is the Pauli exclusion principle, and it just says that each orbital can hold up to 2 electrons with their spins in opposite directions. And so what that means is, when we talk about their spins, we're saying, hey, look, one needs to be up and one needs to be down. I want you to notice that this is showing you half arrows. Some older nomenclature will show half arrows, and some of the newer ones will show both arrows. So just be aware that you can see either of those depending on what you're looking at. So a violation of the Pauli exclusion principle, or what would be incorrect, would be for lithium, would be both of these pointing up, right? That would be incorrect. Another one would be, nope, it would just be pointing up. Okay, so that would be the violation there that you would see for the Pauli exclusion principle. The next rule is Hund's rule. That says that each orbital in a subshell at a certain energy level is half filled with 1 electron before any orbital is completely filled. So what does that mean? I want you to look here. When we are putting electrons into these orbital diagrams, for example, boron has 5 electrons. We've got the 1s orbital here, so 1, 2, we fill it up with 2 electrons. We go to the 2s orbital next because we're following the Aufbau principle where we're going from the lowest energy to the next lowest energy. So we've got 2s here. Then we get over here with 2p and we have 1 electron here. Well, with carbon, we're not going to put that second electron in the 2p in the same orbital here. Instead, we're going to give it its own orbital right here. And so you do this until all the orbitals of the same energy are filled up. So notice here, all of these orbitals get filled up after nitrogen. We're not going to go on to 3s. We're going to go back and we're going to add the second electron to each of these orbitals here. So these are the rules that we are going to follow when we write these orbital diagrams or electron configurations. So let's talk about the process for drawing electron configurations. So the first thing you're going to do is you're going to obtain the total number of electrons in an atom from the atomic number, right? And I want to remind you that's on the periodic table. And then the electrons in the atoms occupy the lowest energy orbitals that are available beginning with 1s, and you fill the subshells according to their lower energy. Now there's a lot of different kind of helpful ways to remember this. This is a really nice one where you write all the 1s, all the s's here. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and then the p's here, and then the d's here, and then the f's here. And you see you keep the 4s in a line and the 5s in a line. And then you draw an arrow and you say, hey, look, we're going to start with the 1s, and then we're going to fill up the 2s, and then the 2p and the 3s, and then the 3p and the 4s, and then the 3d, 4p, 5s, and you follow it around like this. And I used this on my exams when I was a student a lot to help me figure out what order I needed to fill up these orbitals. Remember that the S subshell has 1 orbital. It holds 2 electrons. The P sublevel has 3 orbitals, and they each need to be half filled before you go back. They each need to be half filled. The D sublevel has 5 orbitals, and they also need to be half filled. Another way to do this is using the periodic table. So you see here, this is our 1s, and then we have 2s, and then 2p, and then 3s, and then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, and 5f. These are our lanthanides and our actinides. We've just put them where they're supposed to go in the periodic table. And so this is a really nice way to organize and use the periodic table to help you do these electron configurations. So let's do an example. We are going to look at selenium. So selenium is right here on the periodic table. And the first thing that we're going to do for selenium is the orbital diagram. So when I look at selenium, I see that it has 34 electrons because its atomic number is 34. And so when I need to do the orbital diagram, I could draw boxes, but I learned with lines. So I'm going to draw lines because they do not take as long to draw as boxes, right? And so we're going to start out with the 1s orbital, right? And so when we look here, to get to selenium here, we go through the 1s orbital. We start back over here, we're going to go through the 2s orbital to get to it. So now I'm going to write the 2s orbital. I use my periodic table, I come over here, now we're in the p's, and this is the 2p. It's on the same line as the 2s. So 1, and I know there are 3 orbitals in the p orbitals. I go over here to 3, and now I go to 3s. Okay, I keep using my periodic table trying to get to selenium, and over here is 3p, And I know 3p has 3 orbitals because it's p. And now I'm still following along. I've gotten through the 3p. Now I've got to go through 4s, 3d, and 4p. And so I'm going to go ahead and write those down. And I just want to check to make sure that I didn't leave anything out. And it looks good. So now what I'm going to do is I'm going to go in and I'm going to fill up my electrons. So I've got to fill up 34. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. All right, there's my orbital diagram. Boy, was that a pain. That was a lot of writing. Turns out there's a shorthand for this where we can just write the electron configuration. So when you write the electron configuration, right, you write the orbital. So like, for example, 1s, and then you're going to put a number here. And that number is just the number of electrons. So, for example, I look at 1s. I see there are 2 electrons here. And so that becomes 1s2. I look at 2s. There are 2 electrons there. That's 2s2. The next is 2p. There are 6 electrons there. That's 2p6. 3s2, 3p6, 4s2, 3d10, and then 4p4. But that's still a lot of writing, right? And so one of the further shorthands is the noble gas configuration. And what we do with the noble gas is there's selenium. We go back here and we say, okay, argon is the noble gas that comes before selenium on the periodic table. And so instead of writing all of this business, I just say, hey, look, that is the noble gas. That is the electron configuration for the noble gas argon. So I'm going to come down here and say, hey, look, instead of writing all that, I'm just going to write argon and then write the electron configuration that comes after that. And that's 4s2, 3d10, and 4p4. So we'll work on this more in class. Now, maybe the burning question in your heart is, Dr. Pierce, you've made us learn all this. Why? Well, let's go back to that original question that I asked at the very beginning of all of this, which is, why do some transition metal compounds have color and others don't? And look, this is Cu+, okay? This is copper 2+. One has color and one doesn't. I want us to look at the electron configuration of just copper with no charge. So copper with no charge, if you were to do this electron configuration, copper has 29 electrons. And you would think that copper's electron configuration would be argon 4s2 3d9. But unfortunately, it's not. It doesn't obey the rules because this particular S and this particular D are really close in energy levels. And so what actually happens is for copper, you get argon 4s1 3d10. Okay. Now, when we have copper plus, it has lost an electron. So now it only has 28 electrons. It loses the electron from the s orbital. that's after the Nobel gas configuration. So copper plus is now argon 3d10. If we look at copper 2 plus, copper 2 plus only has 27 electrons. So now we have to remove one other electron. And it is argon 3d9. So look, this, if we were to do the orbital diagram, it would have a full d orbitals. Every single orbital is full in that d shell, right? But here, this is not a full d orbital, right? That's the one that has color. That's the one that's blue. Maybe that empty d orbital matters. Let's look at some other elements. So I have some other elements here that have the approximate colors of some things and things that don't have color. And the take-home message here is these guys, they either have full d orbitals or no electrons in d orbitals. For example, magnesium is not a transition metal with one empty space in a d orbital. This is a group 2, so it's an alkaline earth metal. None of these give us any colors. All of those are colorless. Now look down here. All of these ions, which are shown complexed with water, but when water doesn't have a charge, so it would be like chromium 3 plus, iron 2 plus, cobalt 2 plus, nickel 2 plus, and copper 2 plus. All of these have a color, and they have some electrons in the d orbital, but their d orbital is not full. And so what this suggests is the partly filled d orbital is involved in generating the color in some way, right? And a lot of places will define transition metals as having partly filled d orbitals. So what's going on? Why does this d orbital matter? Well, the reason is if you have an empty d orbital, the atom can undergo something called d to d transitions, right? And so I want us to look at cobalt. So when cobalt is complexed with water, which I'm showing here, it forms this structure, and this is an octahedral complex, okay? And it has 6 ligands that are located around it. Now, we have talked about ligands a little bit in our copper patina lab, and I just want to remind you that a ligand, which is sometimes pronounced as a ligand, is just the molecule around the metal. All right, that's all that means. And so, for example, the ligand is water, okay? So what happens is when the ligand bonds with the transition metal ion, there's a repulsion between the electrons in the ligand and the electrons in the d orbital of the metal ion. And that raises the level, the energy of some of the d orbitals, but not all of them. So what happens is, right, when water complexes or bonds, let's say bonds, that's a better one. When water bonds with the metal, there is a repulsion of electrons, and the d orbitals split, right? Two are at a higher energy. Right? And so because of that repulsion, that raises the energy of two of these orbitals. So they're split into two groups. And if they are not full, then what can happen is an electron can go from this energy level to this energy level. So it can absorb energy. So what happens is the white light will cause the electron to absorb energy and be promoted to the higher energy level. And that allows us to see color. Now, why do we see different colors with different metals? Well, the size of this gap, so the size of the gap between the two energy levels determines the wavelength of light that's absorbed and the color that we see. Now, there are three factors that are important in determining the size of that gap, okay? The first factor is the identity of the ligand. So different ligands have different effects on the energies of the d orbitals of the central atom. So different ligands have different effects on the energies of the d orbitals of the central atom. Okay. So look at this copper complex. So when we made our copper patinas, we started with a copper water complex. And then when we added ammonia or did the ammonia fuming bath, we got a dark blue color. And this was more of a blue-green. I know it was blue, it's blue here, but it was more of a blue-green, right? So this absorbs red light, but this one absorbs yellow light, and that gives us our different colors. And the reason we get different colors is because of the ligands that are attached to it. So some ligands have really strong electrical fields that cause a large energy gap, okay? And others have really weak fields that produce a smaller gap. And so the size of the gap between the d orbitals is what determines the color that we see, that wavelength of light that's going to be absorbed. So this is a list of common ligands that are attached to metal complexes. And those at the top produce the smallest splitting. So they're going to be the really weak field ones with small gaps. So they have a weak field, a small gap, and another way to say that is the smallest splitting, right? And the ones at the bottom have the largest splitting, and they are a lot of times referred to as a strong electrical field or a strong field and large gap. Okay. Now, basically what this means is that these the ones that are farther down need more energy to promote the electron because that gap is big. Right? And so that means they need to absorb shorter wavelengths. Okay. The ones at the top here, they will absorb longer wavelengths. And so as you go down, we'll have a shift from longer wavelengths like red to orange to yellow to green to blues and so on. Now, the exact color depends on what the metal is, right? But let's just look here at these two. So if it's just complexed with water here, and there's water there, and then we change it to ammonia here, and ammonia's there, we are going from a small splitting to a larger splitting. And so this is a longer wavelength than this. So this has a higher energy. It's got that larger splitting. It needs that higher energy light to promote that electron up. And now notice what we see though is the complementary to that. So we see the complementary. And I swear that showed up really as green. So I'm going to try to make that greener on that side because red, the complementary, is green there. All right. So that's the first factor that affects the color of the complex, right? The next one is the charge of the metal. So as the charge increases, so does the amount of the splitting of the d orbitals. So as the charge increases, the splitting also increases, and you can get a shift in color, right? So changes to the charge on the metal are what cause this. This is also known, that charge on the metal is also called sometimes an oxidation state. So you're going to see that as a synonym. So for example, if we have chromium here, the ligands are the same. The only thing that has changed is the charge. That is why we see a color change here. It's because the charge has changed the splitting between those d orbitals. And the final thing that can affect the color of transition metals are the number of ligands. So splitting is greater. If the ion is octahedral, right? Compared to tetrahedral. So tetra means 4, right? So when we look here, right, this would be octahedral, even though it says 6. This would be octahedral. It's because there's 8 faces when you put the H2O around it. The tetra here is 4. And so there's a color difference here because, yes, the identity is changing, but also because it's going from something that's got 6 ligands around it to one that just has 4 around it. So you can't, the problem is, a lot of times you can't isolate what is causing the color to change, because there's so many things that are changing. So, for example, we have both the identity changing here and the number of ligands that are changing that are surrounding it. And so a lot of times when you look between complexes or you compare them, there's more than one thing that's changing. And so that's just something to consider there. All right, that ends for us this particular screencast. We will pick up and talk about clay in our next screencast.